Hi folks, my name is Sherin. I'm a software engineer at Lyft. And today I will be talking about how we incorporated streaming into our machine learning platform and why we need it and all the steps we went through, all the hoops we had to jump to get it to work properly for us. And just an FYI, I've had like 6 cups of coffee to fight jet lag, so if I sprout wings and fly off, that's why. So how many of you have used or have heard of Lyft before? Quite a few of you. And how many of you have used any other ride-sharing service, Uber or? Okay, great. So for those who are not familiar, Lyft is a ride-sharing service that connects passengers with drivers through our platform. So when you use the Lyft app, when you want to go to some place, you open the Lyft app, you enter your destination, and Lyft gives you a few options to get there. You can take a shared ride, you can take a luxury car, and gives you an ETA, a price estimate, and so on. And then when you pick an option, Lyft platform matches you with a nearby driver who takes you to your destination. So as you can imagine, in this whole interaction, in the world of ride sharing, there are a lot of decisions that depend on the most recent state of the world. For example, ETA calculation would depend on traffic, weather, if there is a road closure or an accident, that may impact the ETA. Pricing depends on supply and demand can vary a lot based on the time of the day, based on similar things like weather, traffic. If there's a train cancellation, there may suddenly be a higher demand for Lyft, for example. So to solve all these problems, we use machine learning to make predictions about what ETA should be, pricing should be, and so on. But your machine learning algorithms are only as good as the data that is used to score the algorithms. And that is where streaming comes in. And apart from that, there are a lot of instances like fraud as well that we want to fight, where real-time information is super critical. So talking about fraud, I want to tell you a short story. A story about Alex and Tracy. So Alex is a driver on Lyft, and this is a totally fictional but a totally plausible story. So Alex is a driver on Lyft, and he got a ride request from someone, and he is on his way to pick that person up. And while he is driving, he gets a call from Tracy. And Tracy says, "Hey Alex, you are an amazing driver on our platform, and we want to reward you, so we want to offer you $200. So Alex is obviously really happy, and then he carries on the conversation. Now Tracy says, "But I see that you are in the middle of a ride. You're going to pick someone up. So let me go ahead and cancel your ride from the back end so that you can pull to the side of the road and we can continue this conversation." So at this point, Alex is thinking, Tracy has to be from Lyft if she can cancel my ride from the back end. So he trusts her, they continue this conversation. But at this time, Tracy says, "But wait, before I give you the $200, I want to verify your identity. And I will be sending you a verification code. Can you repeat that to me?" At this point, I guess you all know where this is going. So Tracy is not really a support agent, she's an imposter. And our poor, gullible Alex gives her the verification code, and oops. Now she has access to his driver account, and she can do quite a bit of damage with that. She has access to his bank details, she can take his earnings, and stuff like that. So we want to combat these kind of phishing attacks in real time. And the thing with fraudsters is they keep on changing their schemes, and we want to evolve and keep up with that. So to solve this problem, research scientists at Lyft, they figured out that there is a pattern to this. There is a pattern to all these fraudsters. So if we can fingerprint, if we can find these patterns in their behavior, we may be able to predict when a fraud is going to happen and combat that in real time. For example, in this case, Tracy was actually a passenger. She requested a ride. Then she made driver contact. So in the Lyft app, once you are matched with a driver, you can call the driver through the app. So she did that, and then she canceled the ride. Taken together, these indicate like weird sequence of events which doesn't occur normally. So this is a fingerprint that can tell you a little bit about whether this can be a potential for fraud. So our research scientists decided to turn to deep learning, and they wanted to use convolutional neural networks to find these patterns and act on that. And this is the input that they wanted to give to the convolutional neural network. They wanted to get the last X events or the last X actions a person took on the platform. Historic context was also important because just one-off action doesn't tell you as much. They wanted to look at what the person has been doing in the past. And they needed event time processing. So all these actions needed to be taken in the context of when they actually happened. So this is an example of a situation where real-time features are super important. And for this and many other such use cases, we wanted to make it really easy for our research scientists to be effective at their work and make generation of streaming features super easy. So when we started thinking about building such a platform, so the first step was, what would we use as a stream processing engine? Like, what would be the underlying engine? And for that, we turned towards Flink. Apache Flink is an open source framework. It provides low latency, stateful computations on streaming data. And you can achieve latencies in the order of milliseconds through that. Event time processing is supported, which was really important for us. And what event time processing gives us is replayability, first of all. So you get the same results no matter how many times you play the algorithm on the same set of data. And exactly once processing for correctness. So no matter how many times the data is retried, there is exactly once processing. Then failure recovery was also important. In a distributed system, anything can happen, things go down. We want our system to gracefully recover from that. And the other thing was ease of use. So Flink provides a SQL API. So stateful computations can be specified in terms of SQL, which was really desirable for us. So at Lyft, whenever any action happens on the platform, whenever a user takes any action, events are generated. And I was listening to Benjamin's talk earlier, and he described events in a really excellent way. So events are something that happens. So in this case, for example, someone took a ride at time t0. So that's an event. So these events are generated on the platform. Our event ingestion pipeline ingests all these events. And these are streamed into multiple kinesis streams and also persisted in S3 for offline computation, just to persist it for historic reasons. Now, the other important thing I want to talk about is why event time processing is important and why it's tricky. In a streaming world, why it's tricky to understand the difference between processing and event time. So processing time is the time when your system observes an event, and this time is maintained by the processor itself. So when a processor looks at the event, it looks at the clock, and that's the processing time. Event time, on the other hand, is the time at which an event actually happened. and this is supplied by the event. So your event will come with a timestamp in them. In a perfect world, when there are no latencies, everything is great, our events would be somewhere on this axis. So there is no latency between event time and processing time. But in reality, it will be something more like this 9 over there. So this 9 has an event time of 12:01, but a processing time of 12:08. So our system saw it 7 minutes later. And then things can be like completely out of order, right? Like complete madness, all out of order. So Star Wars episode 4, 5, and 6 came first. I don't know why. And then 1, 2, and 3. So, so what do you do in such a world where things are out of order and there are latencies, unpredictable latencies? Now, suppose we want to calculate integer sum in 2-minute windows. Suppose that's the problem we are trying to solve. In a batch world, suppose you're running a MapReduce job on data, you run that on complete data set. So before you start the program, your data is fully available. So in that situation, it's easy. So our MapReduce program starts looking at the data, and then it slots everything into windows, and then it produces the results once it has seen all the data. So you're sure to receive correct results. But in a streaming world, data is never complete. It's an infinite, constantly arriving set of events. So how do you know how long to wait, or when to finish processing or commit these windows? So for this, the data flow model, which was introduced at Google, they came up with this property of this thing called watermarks. And Apache Flink is actually based on the data flow model. So the simplest way to understand a watermark is the way time flows through a streaming system. So watermarks are like markers that are in your stream along with your data. These watermarks will flow through. And when the system sees the event, a watermark, what it tells the system is, you can stop waiting for events having timestamp smaller than mine. So when the system sees this watermark 12:02, it knows that I should have received everything having a lower timestamp than this. So if there are any windows that need to be committed, I can go ahead and do that. Now, our system, now in the streaming world, whenever the system sees the watermark, it commits results then. So we have low latency. The system doesn't have to wait endlessly. And as a developer, you can choose what your watermarking strategy should be. So if you know that your P99 latency is 5 minutes, you can account for that when generating watermarks. So now we get low latency. We get results as quickly as possible. But still, data can arrive late. Like if your watermark strategy is not conservative enough, or by an off chance when there are backfills happening and data is coming in late, it can still get missed out, like that 9 over there. But Flink has a remedy for this too. So in Flink, you can re-trigger windows when late data arrives. So you can trigger windows once when the system sees the watermark, and then when the late event arrives, it can re-trigger it. So you have low latency with eventual correctness. And this was really desirable for us because we wanted eventually correct data, but we also wanted our system to get results as quickly as possible, even though they were like one-off. So with the engine taken care of, the second thing we started thinking of was the usability. So our users are data scientists and research scientists. And we started thinking about what do they care most. So they care most about model development, about feature engineering, data quality. And probably the least about figuring out compute resources, dealing with all the things related to distributed systems. But often that becomes a bigger chunk of the whole problem. Like they end up spending a lot of time on data collection, data discovery, schematization, compute resources. So we wanted to abstract all that out for them. Then we also started thinking about what a typical machine learning workflow looks like. So a bigger part of the machine learning workflow is the data prep. So finding out what sources are available, cleaning it up, generating features, and only after that comes the modeling and training and evaluation. And the data input and data prep is often the most complicated and time-consuming aspect of doing anything machine learning. So with that in mind, what came about was something that we lovingly call Drift, because every project at Lyft has to have a Y in its name. So this is our self-service streaming framework. And the user plane, which is the only thing that the user interacts with, is a simple UI that accepts a declarative configuration as input. And I will get to that in 1 minute. The control plane does all the heavy lifting of data discovery. It does the query analysis. It figures out how much resources do I need to run this streaming program. It does all of that. And then finally, when features materialize, they are written to several different places, to Kafka, to DynamoDB, which is our main feature storage, Druid for analytics, Hive, and Elasticsearch. The user only needs to give us this. It's as simple as like a one-page declarative configuration. So users can specify their logic in terms of SQL, and which was great because Flink SQL API is really powerful. So almost 90% of our use cases can be expressed in terms of Flink SQL. And then they give us a simple job config, which contains like metadata about the job, what the retention policy should be, where the features need to go, any versioning information, and so on. And this is what a general ecosystem of our streaming service looks like. The blue box on top, that represents a user's application. So when the user gives us the declarative configuration and when they hit submit on the UI, the user application starts. It starts consuming data from the data sources, applies the logic, writes to a kinesis stream. Then a separate feature fan-out job reads data from this kinesis stream and materializes it to all the sinks where it needs to go. And the reason why we had this two-step process is so that user applications can run completely agnostic of where the data needs to go. So that way, our sinks can evolve irrespective of what's happening with the user app. So the feature fan-out job actually does the work of any kind of transformation, manages throughputs to sync. It does everything that's needed to materialize the data. And when we were building this, we also decided to eat our own dog food. So the feature fan-out jobs are also written using Drift's declarative configuration and runs on Flink. And this makes it really easy for us because now anyone, like even in the middle of the night when we get paged, like you're writing too much to DynamoDB, our SREs can go and quickly change a config, lower the write rate, fix any small parameters and quickly update the job, like one touch. So it's really, really, really easy, no coding required. And any kind of transformation can also be expressed in terms of SQL. So even though these feature fan-out jobs are stateless, we can still use SQL for that. Now let's talk about deployment, and this is where things got really interesting and we went through several roadblocks to figure out what worked for us. So previously, until like about a year ago, our platform ran on AWS EC2 instances using our custom deployment. There was basically one big cluster. There was one job manager cluster, and the job manager's only job is to submit jobs or create tasks and submit it to another cluster, which is a task manager cluster. All our jobs, and there were like 60 jobs running on the platform at that time, they were all running on the same cluster. And this is what it looked like. So all the jobs in one cluster. So if one job takes down the whole cluster, all the jobs are down. And it was multi-tenancy hell, as you can imagine. So at this time, Kubernetes came to our rescue. With Kubernetes, now we deploy each application in its own separate cluster. It has its own dedicated job manager pods and task manager pods, and there is separation of concern. So now the problems of the multi-tenancy architecture is removed. Another thing over here that I want to mention. So because it was running on one cluster, compute resources were kind of manually computed. So we would anticipate, okay, by next week, we might have like 60 jobs. If each job needs like a parallelism of 10, maybe we need 600 instances. So we would do these manual calculations. When we deploy, we used to ask for 600 instances, which is obviously not a great use of our time or a good model. So now, so to solve all these problems, we built something called a Flink Kubernetes operator at Lyft, and which is available in open source. So you can find that in the link over there. With Flink Kubernetes operator, this operator is essentially like, you can think of it like a cron job. You provide it a custom resource descriptor. This Kubernetes operator is like constantly polling for custom resource descriptors. It looks for any new custom resource descriptor, any changes, and it basically materializes whatever your desires that you write in that custom resource descriptor into a cluster. A custom resource descriptor looks something like this. So now in one page, you can tell the Flink Kubernetes operator what your cluster should look like. So I can say that my cluster will be running a Flink application. I can give it an image name, and my image will contain all my Docker image will contain all the dependencies. And I can also say that this is my task manager configuration. I want all my task managers to have 15 gigs of memory, 4 CPUs, and so on. And when Flink Kubernetes operator will read that and just make it happen. So if I go back and change this, update this over here, like change the CPU to 1, I don't need to do anything because the Flink Kubernetes operator is constantly listening to these changes. So it will listen to these changes and it will update it. So now this is what our entire deployment step looks like. The user writes a declarative configuration. Our control plane validates this configuration, does query analysis. Based on the query analysis, it figures out how much memory is required, how much CPU, what the parallelism should be, and it generates the Kubernetes CRD. And from there, the Flink Kubernetes operator takes over and it deploys the application, and everything just works fine. So it's all that is completely isolated from the user. With Flink on Kubernetes, as I mentioned, we have each Flink application runs on a separate cluster. We were able to scale to hundreds of Flink applications, and automatic updates as well is supported. And the best thing is resource calculation and allocation is done on a per job basis. Now let's talk about bootstrapping. This was another big problem that we spent a lot of time trying to solve. So first, let's understand what is bootstrapping. So let's look at this simple program. So here we want to count the number of rides a person took over a 30-day period. So the point to note here is this is a streaming application which is reading streaming data, and it wants to count the number of rides over 30 days. So now suppose I start the program today and it starts accumulating data into states. For this job to correctly answer the query, it needs to run for at least 30 days to have enough data to be able to answer this query correctly. And that's definitely not a good solution, because what if after 30 days we realize that, oh, there was something wrong with the logic and we need to update it? So that's definitely not a scalable solution. So what you can do is we can bootstrap the first state looking back using historic information, and then we keep on updating the state as new data comes in through our streams, which is great. In theory, it works really well. The problem arises when the sources that you read from do not have 30 days worth of data, which is often the case. Kinesis has maximum retention, I think, of 7 days, if I'm not wrong. With Kafka, also, it's really expensive to have like really long retention policy. So you cannot have, unless you have an infinite retention source, it's not possible to get all that data from one source, which was the case with us. So what we did was we decided to read from two sources. So we would read real-time data from Kinesis, which has a retention policy of 7 days, and everything else from our S3, which is our historic source. And we retain data in S3 forever. And in order to remove any kind of duplicates, when we are unioning these two streams, we use like a target time as a bridge between when we are unioning this data. And this works great. This is what we currently use. So this is our bootstrapping strategy. Now, one thing to note here is when the job starts, when it is bootstrapping, it is reading like 30 days worth of data all at once from S3. And we see this huge spike in the number of records being processed. Once the bootstrapping is over and it's just processing real-time data, it's now catching, and in real time, it's not at the same, data is not being read at the same rate all at once. So the problem with this is you can clearly see that during bootstrapping, it needs a lot more resources to do its job. And bootstrapping time can vary based on the kind of job it is. So either we could provision the job for the maximum whatever is required for bootstrapping, which is not great, which is a really costly option, or we had to deal with it in some other way. So what we did, we would start the job with a really high parallelism so that it has enough resources to go through this huge backlog of historic data. Then our system would automatically detect when bootstrapping is over. And we do this based on watermarks. So remember the watermarks that I talked about earlier? So our system would keep on listening to the watermarks to see how time is progressing within the streaming system. And when the watermark approaches somewhere within a reasonable limit of real time, we realize that, okay, bootstrapping should be over. And at that time, we update our CRD with fewer resources so that the job update takes place. And then our job can proceed with fewer resources, so we save on cost. Another thing that we had to deal with was the output volume spike. So because during bootstrapping, our job is reading a lot more data, so understandably, it's also producing a lot more data. And how do you manage throughput in that situation? Like, do you over-provision your sinks to handle that huge spike during bootstrapping? That can be a strategy, but that is, again, really costly, like over-provisioning for a short bootstrapping period. So what we did was we realized that for us, feature needs to be fresh, but eventual completeness is okay. So instead of over-provisioning our sinks to handle that really high spiky throughput during the bootstrap phase, we decided to write the data produced during bootstrap into a separate kinesis stream. And then the feature fan-out job that reads from the kinesis stream would smooth it out and write it over a longer period of time. So now our sinks do not have to be over-provisioned to handle that throughput because they are just receiving results in one rate. And the results produced during steady state go through a high priority kinesis, and they are written to an idempotent sink. And it's important for the sink to be idempotent because there are two different sources now writing data to it. So you need a way to make sure the sink knows how to decouple that. Now that is all well and good. Now two obstacles over, another third thing that we had to deal with was the time skew. And that was a really interesting problem that it took us a while to figure out. So let's think about what is happening during bootstrapping. So I mentioned that our program is reading from two sources at the same time. So we are getting really old data from S3, and we are getting like new, fresh, brand new data from Kinesis. Because we union it, all this data is going on and updating windowed state. So suppose our window is like 2-minute windows. All these older data is updating like older 2-minute windows. New data is coming in and updating new 2-minute windows. The challenge arises because of the way watermarks flow through the system. So remember I mentioned watermark is a way time moves through a streaming platform. So watermark will be based on whatever the oldest data is that is being processed right now. So if your system is still processing old data, the watermark will not proceed. Time will not move forward until it is done with that. And because watermark is not proceeding, all these windows are waiting open over there because they are only triggered once based on watermarks. So what we saw was like the state size explosion. Our memory usage just went up because of all these open windows that are just waiting for watermark to proceed. To solve this problem, we built source synchronization into our sources. The way source synchronization works, now each source task that is reading from either Kinesis or S3, they would publish their watermark, their view of the time in the system to a global state, which is accessible to all the consumers, all the consumer tasks. Now each consumer task, when it's reading data from a source, it puts it in a priority queue, and then it looks at the global watermarks and it makes a decision. It looks at the data that it has and it questions itself, like based on this watermark, is this data going to be used soon enough? Like, is my data too new, or is the watermark too behind? And if the watermark is too behind, if the global watermark is too old, it means that I might just forward this data to the other task and the state will be just sitting there and will not be used. So the consumer task just pauses over there. It pauses and then it waits for, it keeps on polling the global watermark state and it waits for time to advance in the system. And when time has advanced beyond a certain point, at that time it starts proceeding with that data. It starts reading from the sources again. So because of this problem, because of this waiting that we introduced, now now our sources wait to produce new data, the time moves forward, and the issue that we saw with memory was removed. Now we have, with all these improvements, we were able to scale the system. And now we have about 120 plus features that are being produced by our system. We write features to DynamoDB and several other things. Now the time to write, test, and deploy a streaming application has reduced considerably. Now our research scientists can write and test and prototype and start off streaming jobs in half a day. And our P99 latencies are 5 seconds. And remember I mentioned that 90% of our use cases are solved by Flink SQL, but not everything is. So we are looking into Python support as well, and for that we are currently looking into Beam. So that may be coming up. With that, I would like to conclude. Thank you so much for attending my talk, and let me know if you have questions.
All right, I see your hand already. Let's start there.
First, thanks for the presentation. Thank you. At the beginning, you said you had a pattern when you wanted to find some frauds. Mm-hmm. Did you find this pattern through machine learning, or is machine learning, or what's the reason for machine learning, if in this case?
Yeah. So the way we train our, so we use produce batch features through Presto and batch queries for training the machine learning algorithms. The streaming feature is actually used for scoring it. So this is the input to our, so the way it works is we have, once our machine learning algorithms are trained and they are deployed in production, we have something called as a model executor. So the model executor knows knows what the model is, and then it needs features to score or as input to the model to make a decision or make a prediction, and that is what the streaming features are used for. So for that we needed like really instant real-time information. So this particular feature, it required like would look at like last 2,000 or so actions and with timestamp. And in this case, there is, I'm not completely sure about what the actual way it finds this pattern is, but this is the data that it would use as an input in production to make the prediction. Yeah.
Some more questions, there we go.
When you're doing the historical sort of backfill and then you're going to reconfigure the job and start it again, do you ever run into issues where your job stores a lot of state and that save point might take a long time, or, I don't know, have issues? Is there any challenges around that transition?
Yeah, so for us, the biggest, so there were like two issues that we saw with that update. So one thing is with Flink, like whenever the job graph changes in any way, like if suppose a new operator is added, something like that, so at that time save points become incompatible. So that was one reason why we kept the job graph the same. So even though in steady state the S3 operator is not doing anything, it's not reading any S3 data, but because just so that we could keep job graph the same, we basically just keep the operator around. So that was one of the issues. Related to state, not really. Our main issues with like checkpoint size was the memory issue, the data skew that I was talking about. So because of that time skew, because of that our checkpoint sizes used to be really high, and then checkpoint alignment would take a long time, and then we saw a lot of issues around that, especially for like really high volume events. Yeah.
Any more questions? Yep.
Hey, thanks. How do you deal with schema changes? Like if some of the people actually change like the query, the SQL query they're actually executing?
Yeah, so the way it works internally, so we have, suppose there is a schema changes that is actually like a breaking change, like it completely makes save points incompatible, checkpoints, and the job cannot proceed. So the way we do that is so the way our features are stored in DynamoDB, they are namespaced under a feature name and a version. So suppose I have a feature that's counting like the number of writes. So suppose the version 1 is running with like schema 1. And I know that the schema change is going to break this. So the way we do it is we re-bootstrap a version 2, which is written under a completely different namespace, and then we automatically cut over the clients. Once it is fully bootstrapped and like caught up, and it has picked up all the updates, we just cut over to the new version. Yeah, no problem.
Any more hands? Don't see any more, but I'm sure Sherin would be very happy to answer any more questions that you have. So if we can give her a warm round of applause, thank you so much.